Okay, well, let's look at the complex eigenvalues. This is part 2 of 8.2. So there is our differential equation, and this is our A. Let's go ahead and find our eigenvalues. It's a -3 there in the first term that I made a mistake on. So we have lambda 1 and lambda 2. We're going to focus on lambda 1. So I'm actually just going to look at this second equation. There's 2 equations there. My second one is x times 1. And I'm going to set y is equal to t, our normal process. So my v1, and it's just 1. So let's write this out. So that's my first eigenvalue vector. And my real part of the eigenvector is 2, 1. And then my imaginary part is 1, 0. It's just the coefficient in the front of each part. And it's a known fact. My v2 is going to be 2 minus I, 1. So simplifying this a little bit, this right here. So just breaking up the 1 plus it. And if you recall Euler's, we're going to use that here and here. Here and here. And adjust it for the second one, of course. So just replacing this with this. So e to the minus it equals and using odd and even functions, this negative goes away, this negative comes in the front. Now I'm going to distribute this to both. Okay, so we're distributing, and it's going to be this times this. Just copied it. And then this times this. So in the front, it'll be I times 2 plus I times 1 times the sine of t. So in front of the sine of t, it's I squared, which is minus 1, plus 2I, and then I on the bottom. So x2 just copying this and then changing this is the negative angle because of the negative. The cosine of negative t is an even function, so that negative disappears. And since sine is an odd function, that negative will go to the front. So now distributing this. That's easy. And then it'll be minus I when I distribute it to the second one times 2 minus I, 1, which is minus 2I plus I squared minus I. which is, whoops, plus minus 1 minus 2i minus I. Erase this and scooch this over to add my sine of t. So now what we're going to do, I'm going to add the two lines, x1 plus x2. Of course, I'm going to add down here. It's e to the t, cosine of t, and then I just add term by term. 2 plus I, 2 minus I, the i's cancel. 1 plus 1 is 2. Plus, I can factor the e to the t out. Sine of t. What happens here? It's minus 2. 0. And I'm basically going to call this, remember this is also a solution, so we'll call this my first solution, x1 star. I'm going to take half of that, just to clear out those even numbers. But I'm actually going to distribute out that negative. And isn't that amazing how all of the imaginaries went away? Yeah. And you might recognize, after I factored that negative out, 2, 1, and 1, 0. Wasn't that the real part and the imaginary part of our first eigenvalue? Yeah, it's pretty cool, huh? Okay, so how do I get our second value? Similarly, I'm going to take x2 minus x1. Subtract them. Up there I added them, now I'm going to subtract them. Up here. This minus that cancels the 2. It's minus 2i. Let's write the cosine first. It's in common. And then 1 minus 1 is 0. This minus this, the 1's cancel, minus 4i, minus I. And so my x2 star so writing them together, and I want to remind you, my vector 1, I did have to find this though. This is my real, this is my imaginary part, which we see up here in all 4 places. So basically, both solutions come from the first vector. Isn't that cray-cray? So in general, this example, where my lambda is equal to, where I had, my lambda equals 1 plus I. We'll call that alpha is 1, beta is 1. That's the real. So here's our actual case 3, which are complex eigenvalues. No, that's imaginary, sorry. Just look up here. They're all V1, just like here. So in our last example, my alpha was 1, my beta was 1. So sine of a single angle, sine and cosine of a single angle, and it was 1t up here. So that's how that would change. So, I mean, I could have given you this without the explanation, but I thought it was a really neat explanation. But you do have to go through and find your complex eigenvalues. You just need one. So let's do an example to see what it looks like. So we're going to rewrite this as x prime equals, so my A, Okay, so lambda 1, we can just look at the 5 plus 3i. That's both of them. Well, we don't really need to augment it because we're just going to set up the second equation so that our x is already isolated. Minus 2x equals 0. We're going to set that equal to my t. Times our t. And we can times that by 2. So again, this is real, this is imaginary, just like I wrote out here. So here's our solution. Alpha is, let's write it out. Lambda equals 5 plus 3i. Alpha equals 5, beta equals 3. Real part is 1, 2. So if we wanted to, we can write this as a matrix too, except it doesn't, I don't know if it looks any better. We have x equals e to the 5t. Oops, that's a plus. With our vector here being cosine of 3t, sine of 3t. So that's the same thing. If you can just see, you multiply this times this, you get that. And then this times this, you get that. It's the same thing. Okay, that's the end.